Hi there, folks. Today we're looking at the golden ratio. The golden ratio is just a special ratio. It appears in a lot of different places. We find it in nature in terms of some examples that we see there. We also utilize it because the golden ratio ends up being very visually appealing when we have things that are modeled after the golden ratio. So we use it in things like architecture and that kind of stuff in order to create things that look a certain way. And so the golden ratio is derived this way. Basically, given the segment AB containing point C, the golden ratio is when AC is the geometric mean of AB and BC. Okay, so when AC is the geometric mean, when this longer piece right here, and so if I kind of wrote it this way, when this longer piece of AC is the geometric mean between the smaller piece and the whole thing. Okay, when that piece is the geometric mean between those other pieces, we end up with this thing called the golden ratio. All right, and the golden ratio is approximately this. It's actually a much longer decimal here, kind of like when we look at things like pi or the number e or that kind of thing. And so the golden ratio, we approximate it just like we approximate pi. So it's 1.618 to 1. All right, and so that's the golden ratio, is that 1.618 to 1. And the nice thing about this is because it's written from the perspective of 1.618 to 1, since it's compared to 1, we can a lot of times find the golden ratio or find the missing value simply by multiplying or dividing by that 1.618, okay? So in the context of where we look at this, we kind of look for the golden ratio in certain situations. So that's one way that we'll kind of talk about this thing. And we'll also try to create shapes that utilize the golden ratio. So if we talk about something like a golden rectangle is a rectangle where the length and width follow the golden ratio. Okay? And so if I look at something like this, this is us just kind of showing where this thing comes from and deriving this guy. But if x is the geometric mean, if we want this thing to be a golden ratio, we would say x is the geometric mean between the smaller piece, which is 1, and the whole thing, which is actually x plus 1. Okay? And so if we create this situation where we want the golden ratio here to kind of find these lengths, here's where this comes from. We cross multiply, so that's going to be an x squared equals x plus 1. And now from here, we want to solve this thing. If we subtract, that's x squared minus x minus 1 equals 0. And then from there, we want to solve this thing. Well, we'd have to solve this thing using our quadratic formula. So opposite of b, plus or minus the square root of b squared minus 4ac, all over 2a. And, this takes a little bit of simplification here. But as we simplify this thing, that's 1 squared negative 1 squared is 1. And then it's going to be plus 4, so that's a 5, all over 2. And now basically there's two things for me to plug into my calculator here. I'm going to do 1 plus the square root of 5. And then divide that by 2. And when I do that, it gives me 1.618033989, okay? And then if I did the subtraction version of this thing, 1 minus the square root of 5, and then again divided by 2, it gives me a negative 0.618033, and so on and so forth. But the idea here is because we're talking about a length, I got to get rid of this other guy. So I'm going to get rid of this thing. I'm going to get rid of this negative. And so the value that I'm left with, well, that's the golden ratio, okay? And so this is where the thing is derived from. If AC is the geometric mean between the smaller piece and the whole thing, I get this decimal that gives me this golden ratio, that gives me this ratio that is visually appealing, that shows up in some natural examples. And we can see the rest of the decimal here. And again, just like something like pi, the never-ending, never-repeating decimal of pi, we approximate as 3.14. Well, this one will approximate as 1.618, okay? Something like this guy, if I want to find the value of x, making this thing a golden ratio, once again, I could set it up as a proportion. I could say, hey, x is the geometric mean. So x is the geometric mean between 5, the little piece, and the whole thing, which is x plus 5. And once again, I could cross multiply and solve this thing. And I would, once again, have to use my quadratic formula to solve this. But because I know I want this thing in the format of the golden ratio, okay, if in the previous example, if we kind of use this as an example, if this is 1.618 compared to 1, well, we simply just have to take this guy and multiply it by 6.18 to get this piece. And so here the shortcut, once we know the golden ratio, we know what we're trying to find, is I can just take the 1.618 and multiply it by the 5 to get what x is supposed to be if I want this thing in terms of the golden ratio. Okay, so 1.618 times the 5, and that gives me an 8.09. Okay. But if we want to construct things in terms of the golden ratio, to get from the smaller piece to the larger piece, I multiply by 1.618. To get from the larger piece to the smaller piece, I divide by 1.618. Okay? And so that's the idea here. If I want to use the golden ratio, instead of having to sit here and set up the geometric mean every time and solve this thing, okay, over here, I simply just memorize the ratio of 1.618, and I use that to either multiply or divide to get to the piece that I need. Okay? Same thing with something like this guy. If I look at this guy, now I have the larger piece. I want to get to the smaller piece. So the shortcut is I just take the 10 and I divide it by the 1.618. Okay? And so if I do that once again on my calculator, it gives me a 6.18 here. So this is 6.18 centimeters. Okay, so if I wanted to split up a line in terms of the golden ratio, and I needed one piece to be 10 centimeters, the other piece would have to be 16.81 centimeters. And again, you could set it up like this. You could say, hey, 10 is the geometric mean between the smaller piece and the whole thing, which is x plus 10. And once again, you could solve this using the quadratic formula, but if we already know the golden ratio, we can just use that to multiply or divide to get from the big piece to the small piece or the small piece to the big piece, okay? Again, small to big, multiply, big to small, divide. If I look at something like this guy, golden rectangles are a rectangle whose ratio of length to width is the golden ratio. So here's a real basic example of this thing. And once again, we can kind of look at this thing from the perspective of similar figures. If all golden rectangles have this same ratio of 1 to 1.618, we can simply multiply to get to any golden rectangle, okay? And so, for example, if I look at something like this guy, it says if a room is a golden rectangle with a length of 20 feet, we want to find the width. And so if I kind of draw a picture of this thing, and if we want to think of this in terms of similar rectangles, so this one, I want this to be 20 feet, and I want to know what this guy is. And so if it's similar to the original, there's two ways I can do this. I can either set up a proportion here. I could say that, hey, the original golden rectangle up there is 1.618, and that would compare to something like the 20 in the new rectangle I have, and then the 1 would compare to the x, and now I cross-multiply and solve and do all this stuff. But again, the shortcut here is just looking at it saying, hey, if I want to go from the big side to the smaller side and it's following the golden ratio, I just have to divide by 1.618. And that's what I do as I solve this thing anyway. Okay, I divide each side by the, in this proportion that I'm solving, I divide each side by the 1.618. And it gives me approximately a 12.36. Okay, again, the shortcut here is just to look at this and say, hey, to get from here to here, to get from the long side to the shorter side, I divide by the golden ratio, by the 1.618. And if I wanted to go from the smaller side to the bigger side, I would multiply by the 1.618. Okay? But again, the idea here is I want I can write the value over here. I want a room that's approximately the golden ratio, because that's the most visually appealing rectangle I'm going to be able to create. Okay? So if you look at this one, it says, given the following golden rectangle with square ABFE, what can you conclude about rectangle FECD? And so I'm looking at this whole rectangle, this whole thing right here, okay, the whole big rectangle, if that's a golden rectangle, to get from the shorter side, which is the one that's given, so right here I'm given the shorter side, to get from the shorter side to the longer side, I simply multiply by the 1.618. And when I do that, it gives me a 6.427. And keep in mind, this thing is a square, so that means this piece is 4, this piece is 4. I can easily find ED now. So if the whole side, AD, is 6.472 and AE is 4, then this piece has to be a 2.472. And so what we want to look at is, well, what can we conclude about this smaller rectangle? Well, it's got a length of 4 and a width of 2.42472. Well, let's look at the ratio of that thing. You can probably take a guess at this, but if I look at the ratio, 4 divided by 2.472, if we divide that on the calculator, we get 1.618. And so when we looked at the ratio, after finding all these different pieces, when I look at the ratio of the two sides of that smaller rectangle, well, it gives me the golden ratio. So FECD is a golden rectangle. And, it's just kind of this neat phenomenon that happens if I take a golden rectangle and cut it using a square. The resulting rectangle is a golden rectangle. If I put another square in this guy, like if I completed a square right here, well, the rectangle that's left down here would be a golden rectangle. And I could keep doing that. I could split this guy into a square and a rectangle, and the thing that would be left down here, this would be a golden rectangle. And so it's kind of this neat phenomenon that happens. So look at this guy, the Fibonacci sequence. The Fibonacci sequence is found by adding the previous consecutive terms to get the next term. So in other words, when you look at this thing, when I look at this first term, the term before it is nothing. And if I do 1 plus nothing, it gives me this next term, which is a 1. And so now if I look at the two terms that I have now, it's a 1 and a 1, and when I add those together, it gives me a 2. And then if I look at the next two terms, the 1 and the 2, those add together to give me a 3. And so on and so forth. To get the next two, now I do 2 plus 3 gives me a 5. 3 plus 5 gives me an 8. 5 plus 8 gives me a 13. See, I could keep this thing going. Now 8 plus 13 gives me a 21, okay? And now 13 plus 21 gives me a 34. This is the Fibonacci sequence, okay? And I could keep doing this for quite some time. I could keep doing this forever. But it's just, hey, take the previous two terms, add them up, that gives you the next term, okay? And so the interesting thing here is find the ratio of each term to the previous term. And so if I did that, each term like the 1 to the previous term, well, that's 1 over 1, which is 1. And then if I do the next one, 2 over 1, that's a 2. And the next term, 3 over 2, which is a 1.5. And then the next one, 5 over 3, which gives me a 1.6 repeating. And then the next one, 8 over 5. And you just plug these into the calculator. That gives me a 1.6. And then the next one, 13 over 8. Sorry, I'm hitting the buttons on my calculator as fast as I can. I get a 1.625. And then if I did the next one, which would be 21 over 13. And hopefully you're looking at this going, something's happening here, and I can kind of see what's going on as we kind of look at this thing, rounded it to 3 decimals, 34 over 21. We can see that as we go through the Fibonacci sequence and look at the ratio of one term to the previous term, I'm getting closer and closer. 1.619. Oh, very close this time. But I'm getting closer and closer to the golden ratio. Maybe one more. Let's see. I might be pretty much there. 55 divided by 34. And if I round this one to 3 decimal places, it does give me the 1.618. Okay, so that idea of looking at something like the Fibonacci sequence, which is kind of a natural occurring sequence, I can see the golden ratio kind of appears within this pattern, okay, as I look at the ratio of one term to the previous term. It's just kind of a neat thing that happens. But again, the golden ratio pops up in all kinds of different places and applications. All right. And we want to explore that because it shows up naturally in certain places, but also it's a very visually appealing ratio that we use in all kinds of things like art and architecture and those kind of things. Okay?